All right, we've put ourselves in a good position now to work with an example that we're going to work with for most of the rest of the day. It's a smoking cessation example, ecological momentary assessment style data collection. And we're going to do a whole series of analysis from n equals 1 to 2 level to cross-classified and trend analysis and time-varying effect TVEM modeling using cross-classified time series analysis. So where are we in the outline? You might be lost here at this point. Well, we are actually at bullet number 3 here. N equals 1 time series analysis. So here's the data description. It's a data that Saul Schiffman was very kind to provide to me. It's described in an article by Shioko in Prevention Science, where she had another TVEM type of approach to this data set. Like I said, a moderate number of time points. Some would say it's high. I would say it's moderate, perhaps. And they are randomly measured during the day. Say 5 times per day is what they aim, and there are random prompts across the day from a personal digital assistant. So not fixed time points, but random, which causes time interval issues. The outcome variable that we're going to focus on is smoking urge on a 11-point scale. And we're going to relate smoking urge to negative affects, which is an average of 10 items having to do with being unhappy, irritable, miserable, tense, discontent, frustrated, angry, sad, which you imagine have something to do with trying to quit smoking. We're going to relate it to gender, age, and an outcome variable, quitting or relapsing, successfully quitting smoking or relapsing. So we have 2 subjects that I picked out for n equals 1 analysis, just to illustrate what you can see in the data. And this is plots that come out of Mplus. Here's a subject who actually didn't quit, smoking urge on the y-axis and time on the x-axis. You see that the smoking urge tends to go up over time. Somebody who just can't get off the cigarettes. And the smoking level is pretty high, and compared to the subject number 5, the horizontal line here is lower here than here. And the variation is pretty high as well. So the mean and the variance is actually higher than for subject 5. The autocorrelation is fairly small for data that jumps up and down like that. So the autocorrelation is much smaller here than here. The autocorrelation here is higher, perhaps mostly because we have a trend. Trend tends to increase or inflate the autocorrelation. So mean variance and autocorrelation vary across these 2 people. And we're actually going to see a 4th source number 4, for parameters that vary across subjects. Here we have the output from the Mplus analysis. And we see here that urge is regressed on urge at the previous time point. That's what Ellen described. But it's also regressed on negative affect. And we have an intercept, and we have a residual variance. So you see, for instance, that the intercept, this is for subject 227, is higher than the intercept for subject 5. That's what we saw in the data. The residual variance is higher for subject 227 than it is for subject 5. The autocorrelation is lower for subject 227 than it is for subject 5. And the 4th component that's different is the regression coefficient on y, on x, so to speak, is higher and significant for subject 227, but negative and insignificant for subject 5. So 4 things that vary. So this can be fun, you can just scroll through the data and do these kinds of plots. Now, one issue that comes up is this t-interval matter, because the time points are random. So these two individuals don't have the same distance between their different time points. And you want to take that into account because that affects if nothing else, the autocorrelation. So we want to create a new time variable and insert missing data records to align data with respect to time. They're misaligned, we want to align them. The need for alignment could be due to missed measurement occasions that are not assigned a missing value flag, or in this case, due to random measurement occasions. I'm going to show you an example of that. The creation of this new time variable should really be built on both substantive and statistical considerations. Substantive meaning what's a good time distance to consider, what makes substantive sense in terms of what relevant development has had sufficient time to occur. This is described in very technical terms here in the paper, and Tiamer is going to talk about this from a technical point of view tomorrow morning. But here is my take on approximately how it works. And this is for one subject now, a single subject. Observed time given in fractions of a day. Observed time being this column. It goes from early in the morning to late at night. Fraction of, 24 hours. So we're going to work with an interval of 0.08, which is approximately 2 hours. 2 divided by 24, you're going to divide by 24 quite a lot in the future, I promise you. 0.0833, the bin size therefore is 0.08. What is meant by bin? Well, here are the bins. The lowest bin is 0.28 to 0.36 because the difference is 0.08. And we chose that bin because the midpoint of that corresponds to the lowest observed time value. We give that time value the new time value 1. And that outcome is observed at that time. If the next observed time, 39, fits into that bin, 51 fits in that, 59 fits in that, etc. But here, we have nobody who fits into that bin. The bins are all the same. So we have nobody in that bin, so the new time value of 6 doesn't have an outcome that's observed, so we put in missing there instead. And then this value falls into that bin, so that gets time value of 7, and we use the observed outcome for that. The next slot is missing, so the outcome is recorded as missing. So 0.32 times 24 is 7:41 in the morning, which is the midpoint of the first bin. So I think that's approximately right. I checked with one of our programmers, and Thuy Nguyen, who agreed that was what she understood that Tiamer asked her to do. So if you do this now, inserting these missing data records for subject 5, the one who quit, and plot it, you see that there are holes here and there in the development. This layout, by the way, is designed by Ellen Hamacher. She can be very good in suggesting. What do you think I was going to say? Demanding? No. Now, so you see the holes here, but don't worry too much about choosing the right way of inserting missing values. If you don't insert missing values for this subject, the urge on urge lag 1 is the estimate we saw on the previous slide here, and the urge on negative affect is this. If you do this t interval 0.08 binning and introducing missing data, then you get fairly similar results, significant at the same point. All right. How do you do n equals 1 analysis in Mplus? Well, it's very simple. Ellen described most of this. You have a lag for urge, lag 1. And you can have higher lags. Here's the t interval option, where you decide how precise or how wide the binning should be. This is what Ellen referred to as the bin, and tomorrow morning, Tiamer is going to talk about this as delta. And the only thing new really here is that we use observation to pick only subject 5. That gives you the n equals 1 analysis. That's the only thing that's different from n greater than 1 analysis, except that we don't ask for a two-level, type equals two-level analysis. It's type equals single-level analysis. But we do a regression of urge on urge, lag 1, and negative affect. So I guess the two things are different. Use observations, and it's not two-level, it's single-level. So we don't have to say type equals two-level. It defaults to single-level.